Okay, so in your homework, you built an accumulation function, which is essentially how much you have at any moment, or how much has built up, or how much has built up at every moment. Okay? So what'd you do? You said, so at 0 days, how much oil had accumulated? 0. Okay, I think I'm finally ready. So at 0 days, how much oil had accumulated? 0. And so this is that point. 0 days independent, 0 meters cubed of oil dependent. Okay, and then we said 0.4 days later, we approximated the rate of change at about 28, right? And so then what did we say? We said the change in the amount of oil would be the rate times the change in time, right? 28 times 0.4, 11.2. So that's at 0.4 days now. How much oil has accumulated in the ocean or leaked out of the rig? 11.2. And how did it get from there to there? We're assuming at this constant rate of 28. So what are all those correspondence points in between? All those correspondence points in between form? Straight line. So now it's going to take me too long. It's the best straight line I've drawn all day. Okay? It's going to take me too long to draw all those points, so we just sweep. And what does that represent? It represents all the correspondence points of time in days and amount of oil from 0 to 0.4 days. So that's a bunch of points. Time in days and amount of oil spilled into the ocean. So now we're at 11.2, and now the rate changes, right? We're going to assume a new constant rate for the next interval of 17, and so we get that amount of change, right? This is, what principle is this right here that I'm showing right here? We got 11.2 plus 17 times 0.4. What general principle is that? Can you articulate it? Where's Anessa? Bajark? Anessa? How about Eden? Eden God? Yeah. What general principle is this calculation an example of? 11.2 plus 17 times 0.4. Okay, so can you be more specific? What's the 11.2 and what's the 17 times 0.4? And what are we doing in that?
So the 11.2 was the amount we had up to that point.
Right?
And then the 17 times 0.4 is the amount that's being added to it.
The change. Excellent. Right. So it's the y initial plus dy, right? Y initial plus the change. Gives me what? So yeah, so remember this, we've seen this a million times now. Y initial plus the change, which we get by rate times change in x, gives me the final. So the final at 0.8 is 18. Which I think is right about there. Slightly lower rate. So how does that show up? Am I in the right place? Yep, so it's just almost the same, but slightly. That was not the best one today. Let's see if we can do better. Good enough, okay? Again, so now what do we have? Now we have a current total amount. That becomes our initial amount in the next. So our initial amount of 18 plus the change. Now we're up to 21.2 at where? 1.2? 21.2. Okay? And then, again, so again, at 21.2 becomes the initial amount for the next, right? Becomes the initial amount for the next interval plus the change. 21.68 at 1.6. Question?
Yeah, why are you multiplying 1.2 times 0.4? Because 1.2 is the time you were at, whereas like the rate that we found was...
So that's a misprint. Thank you. I was just seeing if you were paying attention. What was the rate that we said for that one? 4?
No,
3. It was 3 and then 4. That's right. 3 and then you should have been thinking this. Not just one person. Should have noticed. Okay, so our rates were 8, then 3, then 4. Okay, so that gives me what, 22.4 at 1 point, where am I up to now? 1.6, 22.4. And then, finally, again, starting, so that should be 22.4 now. What is this? Now this is the initial amount in the new interval plus the change for the new interval, which is our constant rate times the change in x. 24 at, is it 2 now? Just under 5. Oh, so now it's gonna be a little steeper this time, right? Not that steep, but you get the picture. Okay. Okay, so now your charge, now we got the picture, and we just based on those endpoints, but what about can we write a relationship for every single value at time and days? Can we get this accumulated amount? And so what are we going to do? We're going to look at arbitrary points, right? And what do we got? So that point right there represents every point on this segment. So we can call it what? If that represents every point in that segment, what should we call it?
X comma y.
Right, x comma y, right? So it's going to represent every point there, so x comma y. And we want to get that. And so what are we after? We're after what y is, right? That's what this function gives. The function gives the accumulated amount. That's the same as y in my ordered pair there. So y equals what? Y equals the starting value, which is starting value of oil, 0 plus 11.2? No, this could be any point on here. So I need the change in y, which we calculated by
X minus.
all right, so what do I need? I need that process that we've done so many times. Starts with what?
Rates.
Starts with what? The change in x. What's the change in x from 0 to this arbitrary point x? X minus 0. And from that change in x, we get what? The change in y. How do we get the change in y from the change in x? Constant rate of change, right? We're at a constant rate of change. So changes in y are constant rate times change in x. Is everyone 100% tuned in? Lots of times students don't take notes when I'm going over a homework problem. It's just as valid to take notes when I'm going over a homework problem than when I say, okay, new stuff. So whatever you need to be fully tuned in, and you're going to retain this, okay? Because this is super important. Okay, so this is dy, and we're going to get it from our constant rate of change, which is 28 times dx, and we just said our dx was x minus 0. So this is going to be 28 times x minus 0. Okay, and then that's going to be from what to what? 0 to 0.4. Now, remember when I said we want to, so in this region we're going to include both sides, okay? So in this particular interval, we'll have equals on both. But from here on out, we're going to do equals on the right side of the interval and not equal on the left. We said that was kind of counterintuitive because of how we built the rate function. We're going to see in a second why we're doing this. Okay, next interval. So now we need an arbitrary point here. So I'll do it in blue. So xy. And again, in this second line, I'm after this. What is this value of y? Where does it start? Where does it start? With this process, to get that value of y, we start with what? Where's Christopher? Hung. Yeah. What am I going to start with if I want to get that value of y? I'll give you a hint.
dx.
dx. And so now what is this dx? What is that dx right there?
That's 0.4 plus yes, or y, actually f minus 0.4.
Good. X minus 0.4. Do you see that? So in the second interval, our dx now is referenced from 0.4, so it's going to be finalized initial x minus 0.4. Okay? And where do we go from there? Where is Kyle? Arcacello. Kyle A. That's you right there, okay?
Yeah.
I knew that. Just forgot. Okay, where do we go from there? So I got the change in x in the second interval.
So then you need to figure out what your constant rate of change was, which was 17.
Okay.
And multiply that by your change in x.
To get?
17.
What is it? What is it we're after here?
dy over dx, which is constant rate of change.
No, we have it. That's 17. So what do we need? What are we trying to get from here? We're trying to get
dy.
dy, right? dy, which is
mdx.
mdx, our 17. So here's our change in y. And what do we have to do next?
Then you have to add your initial.
Add my initial y. And so what do we get? In this second interval, again, here it is again. Final y equals initial. And notice the initial y in this interval is the same as the what? The final y, the total, the final y in the other interval, at the very end of the interval. Okay? And then that's going to be from 0.4 to 0.8. Okay, I'll go back to red. Let's practice one more time. So if I'm going to model all these correspondence points, I take an arbitrary point. I take an arbitrary point, and what do I do first? Where is Tom, Annette? Tony, is it Tony? Tom? Sorry. Annette, Tom, of course. So what am I going to do first?
The change in x is x minus 0.8.
Good.
And then the dy and times dx
Uh-huh.
is 8.
8 times.
The change.
There's my change in amount accumulated, right?
And then the initial value is 18.
18 is how much I've accumulated in the first two intervals, right? So it's how much, so look at this. This is what we're talking about today. This is how much has been accumulated what? In the completed intervals prior to the current interval. So we're going to say that we've completed 2 intervals so far. And now our current interval is the third interval. And so we have the total amount of oil from the completed intervals plus how much oil we have in the current interval, and that changes, right? It changes according to how far we are in the interval, which is?
dx.
dx is the amount of change in the current interval. dx is the amount of change in the current interval, and we're going to take the amount of change of y by multiplying dx times the constant rate and add that to all the change from all the completed intervals before. So that's new terminology. It's going to be really important. And this is from 0.8 less than x less than or equal to 1.2. So, and the rest continues like that. We got 2 more to go, and for time's sake, we won't do them. Okay, so really important. Not that you can just get the answer, get all the numbers right, but that every piece has meaning, and you are fully aware and understand all the pieces of this. And we keep using this process, these 2 core principles of constant rate of change in everything we do. That the change in y, a little change in accumulation, is a constant rate times a little change in our independent variable. We've lived, this is the land we're living in for the last 2 weeks, and then final amount equals initial amount plus the change. Right? So these are our core principles of constant rate. And they're not going away anytime soon. Yeah.
Your dx one is just for the x minus.
Just this part. Right. And then, so what is it with the 8? What is it with the 8 then? dy, right? Then the whole thing there is dy. Okay, any questions? Okay, but now, so remember what all these numbers, these constant rates, we just eyeballed those off the y-axis on a rate graph, right? Do we have exact values of those rates of change? Or could we represent them?
Yes.
We sure could. How could we represent these exactly? How do we represent that rather than estimating at 28, how do we represent it exactly? Do you remember?
R sub v.
It was the r sub v function. R sub v of what?
0.
R sub v of 0. But actually, let's take that a step further. Hold on a sec. So we'll go back here. So I'll just come over here. Let's recreate that that rate function that we had, and we're going to use that instead. Can't get any further. This is r of x. Okay, so that was r of x, and what do we say? That was rv of 0 from 0 to 0.4, and it was rv of 0.4 for this whole interval. Okay, and then finally, the next one here for the next interval, r sub v of 0.8, and that was the constant rate we used for the whole interval, and then we called this function r, right? R is our approximate rate, these blue steps up here, and that was from 0.8 to 1.2. Okay. But look, what is RV of 0 from 0 to 0.4? What is RV of 0 from 0 to 0.4? What is it? RV of 0 from 0 to 0.4 equals? It's just R of x, right? That's how we're defining R of x. R of x is from 0 to 0.4 is RV of 0. So that's what we need. So all we need to do here is put R of x. And that's that constant rate, right? It's that constant rate in the first interval of RV of 0. What about in the second? R of x, right? So this is why we defined R of x. So we can just easily use it. It will change as we need it to change, right? It will change and be the right constant rate as we need it to. Okay, so now in the next example, we're going to, so this is all what? These numbers were based on our approximate rates, 28, 17, and 8. So in our next example, we want to do this symbolically and have it exact according to R. Does that make sense? These numbers were based on these approximate, 28, 17, 8. And it's a good thing to do, so we saw where those numbers came from. But now in our next example, when we get to the accumulation function, we want to write these in terms of R. We want to write these totals in terms of R. That's where we're going next. Instead of using these estimated values off the y-axis for the rate to generate those total amounts of accumulation. Okay, questions on this example? Questions on this example? Yeah?
How can we write R of x when, so for the second one, you know how it's RV of 0.4,
Uh-huh.
but our x is not 0.4, we don't do 0.4?
It's every x between, so R of x from 0.4 to 0.8 is every x from 0.4 to 0.8. And so, but that rate is that constant value, this constant value that whole way, no matter what x is.
But when we put x over there, we know that x is greater than 0.4, but not equal to 0.4.
That's right.
Wouldn't that be wrong? It is
No, but we define the function as the rate at 0.4, but we just don't start till just to the right of 0.4. Yeah.
So like on the equation or the expression on the right side, you wouldn't put 11.2 though, right? Because we don't know for sure if it's 11.
That's exactly. So these 11.2 and the 18, it's not a 4, that's just plus. Yeah, those what? Those are kind of don't apply anymore now that I'm using this rate function, right? Because those came from our approximate rates, and we built those up with these approximate calculations. But what we want to do is we want to use, we want to get a running total using our rate function instead of the approximate rates. And we'll do that in the next example. But we'll just leave it like that for now on this one. Okay, other questions? Okay, so here we go. So you read about the rocket-powered basketball for Monday. We're going to talk about that. Last chance on this. Okay. So let's just get oriented to the situation, right? When you come to new problems, new situation, new context, we don't just dive in for numbers and equation and try to get answers. Those days are long gone. We want to orient ourselves to the situation. So what we have here is, well, let's orient ourselves to the situation by me asking you some questions, okay? So first question is, this function over here has the name v. That's the function v. So what I want you to think about, don't blurt it out, everyone think about it. What kind of function is v? All right, and so up here it says it's velocity, meters per second, time in seconds. Is that a rate of change or accumulation? Everyone think about it. And so then after asking that question, what are its dependent and independent quantities? Take 20 seconds to think for a moment, and then talk to the person next to you. What's the function v, rate of change or accumulation? And what are its independent and dependent quantities? Go. Okay. Jacob on. No, other Jacob. Jacob, what kind of function do you think v is? Rate of change or accumulation?
I believe it is accumulation.
Accumulation? Okay. Kyle Klein. Kyle number 2. Kyle Klein.
Did I get that right? Or?
We're going to find out. Where's Marisol Sanchez? Marisol. What do you think? He said accumulation. Agree or disagree? You think it's rate of change? And why do you think it's rate of change? Okay? Yeah, so what do we say? Rate of change is like how fast something is changing. How fast something is changing. So velocity, meters per second, does that show us how fast something is changing? How fast? Okay, you're right. So this is rate of change. So what are the dependent and independent quantities for that v function? The v function. So where is Elizabeth? Bria. Where's Elizabeth? Not here? How about Emmy Paul? Emmy? What are the dependent and independent quantities of this function v? This function v, this rate of change function v. What's the independent quantity and what's the dependent quantity? Was Emmy here? Right there, okay. Dependent is time, and what about independent? So where do we normally see independent? On the horizontal or vertical axis? Horizontal. So that would be, yeah. So you had to switch, right? So Independent quantity would be time since the launch of the rocket basketball. And our dependent quantity would be velocity, or rate of change. Rate of change of what? Rate of change of what? Rate of change of speed? No, speed is rate of change, right? Rate of change of what? The height, right? So yeah, either. So distance traveled, but that's distance traveled up, so that's height. Okay? So V is rate of change. It relates the velocity of the rocket dependent to the time elapsed since launch. Okay, so we want to develop the accumulation function associated with V, right? This is this journey we're on. We know how fast something is changing. We want to know how much of it we have. So what are the independent and dependent quantities of the accumulation function that we would want to get from this rate of change function? Or create, build. Go, 30 seconds. Independent and dependent. Okay, where's Christopher Woodward? Christopher, what do you think? Independent quantity for our accumulation function would be? So he says still be time. Agree? Yep. So our independent quantity will stay the same. So because so our independent quantity will stay the same, so it'll be time since the launch. And what about dependent? Velocity would be the dependent quantity of our accumulation function. You're shaking your head. Tell me. Okay, so you said it'll just be meters. Yeah, so that is the quantity of height, right? So what? So we know how fast the rocket's moving, or how fast its height is changing. We want to know what its height is. That's what we mean by an accumulation function in this setting. By accumulation, we mean we want to know actual height, or accumulation of bits of height at any given time in seconds, given that we know the speed profile, the rate of change profile of it. Okay. So accumulation function h gives the height of the rocket dependent as a function of the time elapsed, independent. Okay, that's what we said. New set of questions. Take a minute. So I want to express the coordinates of the point on the given graph, on the left graph. When t equals 5, what does v of 5 represent? And what does v of 5 mean for values associated with the accumulation function? Go. 3 questions. Go. Yes. Yes. That has changed, and I need to put I'll put a top hat question. Thanks for reminding me. I did need to talk about that. Thank you so much. Okay, how can I express the coordinates? Where is Henry Wise? Where's Henry? Right down there. Okay, I want to express the coordinates of the point on that graph when t equals 5. He wants 5 and v of 5. Agree with that? 5, v of 5, okay. And your follow-up question, what does the value of v of 5 represent? What would that represent?
5 seconds, the velocity
Okay, so in what part of all that you said there was the just v of 5? So that was the whole ordered pair. So v of 5 represents Right, so it represents what? The rate of change or the speed at 5, and you said that was about, you tried to estimate it, which is fine. Something like 7 or something like that. Yeah, it's the rate of change of the rocket's height at the moment t equals 5 seconds, okay? So, and remember, at the moment, right? So in order for it to be a rate of change, we need to have a little change. It's not at the instant 5 seconds, but for a moment, around 5 seconds, it's the rate of change of the rocket's height. Okay, here's the golden question. I hope that we have all learned this. Where is Han Shi? Han, can you tell me, what does that rate of change, that value v of 5, whatever it is, what does it mean? What does the value of v of 5 mean? I can't hear you, sorry. Can you talk a little louder? Not sure. Behind him, you were animated. Tell me, yeah, behind him in the corner. Yeah, what's your name? Okay, what do you think v of 5 means? So yes, v of 5 is the rate of change, and what does that value v of 5 mean? Okay, so it is the total change in height? The rate of change is the change in height? That's what I heard you say. It's the height in meters. The rate of change is the height. Where is Lillian Zarici? Can you tell me what that value, that rate of change v of 5 means? It's the same as the height. The rate of change is the same as the height. Okay, how about, we'll keep trying here. Where's Jerome Woodland? Jerome, what does that value of rate of change mean? V of 5.
It means that at that time,
Okay.
or around that moment,
Yep.
that rate is essentially constant.
Okay.
Or v of 5.
That's true. Okay, that's true. And what does that value mean? That rate of change value mean? Where is Ania Holland? Henry Wise again. Where's Henry? Sometimes you get twice in the same day. Where's Henry? Well, he wasn't here the first. Oh, there he is. Oh, you answered the first two. We're back to Henry. Any idea? Okay, you guys, the meaning of constant rate of change. You're breaking my heart. Yes, sir.
Okay, so at the moment at t equals 5 seconds, v of 5 would be, it's the rate of change, so you multiply the rate of change by some differential in x to get the height.
To get the height?
Or to get the change in height.
Okay, yeah, he's onto it, right? So, given any what? Change in time, the change in height is v of 5 times that change in time. We need to have a recap, review homework assignment on this, okay? But this is crucially important. It means that the changes in height, a change in height of the rocket is v of 5 times the corresponding change in time. Now there's a qualification. What's the qualification on this?
Very small.
Very small what?
Very small moment time.
Yeah, so it's only going to be true for a moment around 5 because this is a changing rate, right? It's a changing rate. As soon as we get away from 5 too far, that v of 5 doesn't hold anymore. So this only holds now for a small moment around 5, okay? And so we see that is d8. This is how we get meaning of that value v of 5, this formula, that given a change in time, the corresponding change in height will be v of 5 times that change in time. We'll just keep working on it. All right. So where are we at? Let me do this. No. All right, so we'll pick this